Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 2 on vertical shifting of functions. Now, in our first lesson in this unit, we looked at what were called parent functions, right? Simple functions that we will use then to build more complicated functions. And one of the first things that we're going to be doing is looking at how we can take any function at all, whether it's simple or complex, and how we can move it simply vertically. We just take the function and we just move it up a few units or move it down a few units. How do we do that with formulas? What does it mean? What does it tell us? Things like that. So that's what we're going to be getting into in today's lesson. So let's get in there. Building new functions. We can build new functions from older ones by the use of transformations. Perhaps the simplest of all transformations is the vertical shift of a function, simply moving it up or down, but not left or right, not changing its shape or anything like that. So let's take a look in exercise 1 at how we can transform vertically a simple parabola. Let's take a look. The function f of x equals x squared is shown graphed on the grid. The function g of x is defined by the formula f of x plus 3. Write a formula in terms of x for the function g of x. All right. This is simple, right? So here's a formula for g of x. G of x equals f of x plus 3. But keep in mind, one of the most important ideas in all of math, bar none, is what's known as the substitution property of equality. If I've got two things that are equal, like f of x equals x squared, then anytime I see an f of x, I can put in x squared because f of x equals x squared. They are the same thing. That's what the equals sign tells you. So a formula for g of x is very simple. G of x equals x squared plus 3. All right, all I'm doing is replacing f of x with what it's equal to. All right, letter B. Graph g of x on the same grid as f of x. Show a table of values in the space to the right. All right, let's see if we can actually create this table of values without having to pull the calculator out yet. Right? Let's do it. Now, I'm going to try to do this. Actually, I should say g of x here. I shouldn't say f of x. I'm going to do this, right, by trying to just sort of do the arithmetic in my head. Now, think about it, right? What is g of x asking us to do? It's saying take the input, multiply by itself, right? Square it, and add 3. So I do -3, I square it, and I get 9. Then I add 3, and I get 12. Right? Now that may not even fit on our plot, but that's okay. We'll live with it. Okay, so now for -2. Right? I take -2 and I square it and I get +4 and I add 3 and I get 7. Right? -1 squared is 1 plus 3 gives me 4. All right. 0 squared is 0, right? 0 times 0 is 0 plus 3 gives me 3. Right? 1 squared, 1 times 1 is 1, plus 3 is 4. Notice we're seeing that symmetry that we always get with parabolas. 2 squared is 4, plus 3 is 7. And 3 squared is 9, plus 3 is 12. Now, because of the size of my grid, it's going to be hard to plot the -3, 12, but I'm going to take a shot at it anyway. There's 10, 11, 12. That would be somewhere up here. -2, 7, that'll fit on my grid, is right there. Hold on. Yeah. -2, 7 is right there. My apologies. -1, 4 is right there. 0, 3 is right there. 1, 4, right there. 2, 7. And 3, 12 would be, 312 would be about right up there. So I get this, and I'm going to just label that with g of x. Okay, simple enough. Now, letter C is probably the most important part of this problem. Describe how the graph of g of x compares to the graph of f of x. Well, take a look, right? If I take a look at any given point, right, on either one of these, like let's take a look at the turning point. Here the turning point is at 0, 0. Here's the turning point at 0, 3. What happened to that? Well, I just moved it up 1, 2, 3 units. Likewise, here I have the point negative 1, 1. Now it's the point negative 1, 4. I literally took that point and I just moved it up 3 units. Here I took this point and moved it up 3 units. This one's a little bit harder because it's at a y value of 9, but that y value of 9 moved up to a y value of 12. Every single point on g of x is the same point on f of x. It's just been moved up 3 units. That just can't be much of a surprise, right? You know, ultimately speaking, there's the function f of x, right? Let me try to cover it up that way. There's my function f of x. And then what happens? I add 3 to every y value, so it just moves every y value up 3 units. So g of x is f of x moved up 3 units. It's that simple, right? By adding 3 onto my old function, I took its graph and just moved it up 3 units. That's it. My old function was f of x equals x squared. My new function is g of x equals x squared plus 3. I move it up 3 units. Let's take a look at letter D. How would the graph of h of x equals x squared minus 4 compare to the graph of f of x equals x squared? Produce a graph of h of x on the same grid using your answer to this question. Well, let's talk about this, right? Our original function is y equals x squared, or f of x equals x squared, right? It's just that. As soon as I subtract 4, every y value is going to move down 4 units, right? So h of x will be f of x moved down 4 units. I don't even need to now create a table of values. I can now take my graph, right? Now remember, f of x is the one that's drawn in black, right? It's not the one that I just plotted. And I can take every point on it and just move it down 4 units. So I take this point and I go 1, 2, 3, 4, and it's here. This point, 1, 2, 3, 4, and it's here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. And this is now the graph of h of x. It's so simple to vertically shift or translate or move, whatever fancy word you want to use, a function. And in fact, here it is, right? Vertical shifting of a function. If k is a positive number, then g of x equals f of x plus k represents an upward shift by k units, and g of x equals f of x minus k represents a downward shift of f of x by k units. Now I know stuff like this can seem very, very sort of like, oh God, man, there's letters everywhere, right? But ultimately speaking, it boils down to this. If you take a function and you add a positive number to the overall function, it's going to move that function up. And if you subtract from that function, it's going to move that function down. And we don't even have to have a formula for the function. Take a look at exercise number 2. The graph of f of x is shown. The graph of g of x is defined by the formula g of x equals f of x minus 3. What is the value of g of negative 4? Show how you found it. Well, just for a moment, forget about shifting, right? Let's evaluate g of negative 4 using function notation, right? We know that g of negative 4 must be equal to f of negative 4 minus 3. That is simply the definition of g of x. Then, of course, we can figure out what f of negative 4 is by going over to the graph, going to x equals negative 4, and going up here, and I see that f of negative 4 is equal to 8, right? So substitution property of equality, I'll just put in 8 for f of negative 4. And g of negative 4 is equal to 5, right? So literally, right, the point -4, 5, right? So now let me erase that. -4, 5 lies on this graph. And really, what has that done? It's taken this point and it's moved it down 3 units, right? And that pretty much explains letter B. How will the graph of g of x compare to that of f of x? Well, why don't you write something down for that? All right, well, g of x will simply be f of x shifted down or moved down 3 units. G of x will be f of x moved down 3 units. That's it. And again, a lot of times we use the term shift or translate, all right? But it's also okay to just use the word move or moved. G of x will be moved down 3 units. That now gives us the recipe for how to do letter C, where it asks us to create a graph of g of x on the same grid. Well, again, every single point on this graph we're now going to take and just go, right? We're just going to move it down 3 units, and we've already done it to this point. Go ahead and do it to this point, and that point, and then connect them with straight line segments. Pause the video now and go ahead and produce a graph of g of x. All right, here we go. So for this particular point, I'm going to move it down 1, 2, 3. For this point, 1, 2, 3, 1, 2, 3. And I really should use a nice straight edge on this, but I'm going to freehand it for now, just to speed things up. And now we have g of x. Here's f of x, and there's g of x. Simple, right? And it really is the simplest of all transformations of functions, because we're literally taking the outputs from the original function, which are the y values, right? Not the x values. And we're either adding or subtracting some number from them, which of course leaves the x value alone, but then takes the y value and either increases it, which moves it up, or decreases it, which moves it down. It's that simple. Okay, so any function, even more complex ones, can be shifted up or down based on adding or subtracting the amount of the shift. So let's take a look at this for a little bit more complicated function. Exercise number 3. The function f of x equals x squared minus 6x plus 5 is shown graphed on the grid. The function g of x is defined by the formula g of x equals f of x plus 4. Letter A, give a formula for g of x in terms of x. All right. Well, again, this is pretty simple. All I need to do is take this function, right, f of x, and add 4 to it, right? So the function for g of x is very simple. G of x is equal to x squared minus 6x plus 5 plus 4. And let me simplify this a little bit. X squared minus 6x plus 9, right? That is my formula for g of x, because all I did was take my formula for f of x and add 4 to it, and the only thing that changes then is that that 5 and the 4 combine to be 9. Now letter B. How will the graph of g of x compare to that of f of x? Okay, well, g of x is f of x plus 4, so see if you can answer the question how g of x will compare to that of f of x. All right, well, g of x is going to be f of x shifted or moved up 4 units. I'll use the word shifted this time. Shifted up 4 units. Awesome. Now, letter C, using your answer to B, graph g of x on the same grid. Awesome. Well, there's a lot of points on this particular graph. What you want to do is find nice points, right? Points that go through integer locations, and then every one of those points that you find that's nice, just move them up 4 units, and then plot your new parabola. Pause the video now and go ahead and do that. All right, here we go. Well, this one's nice. So this point at 0, 5 will now be 1, 2, 3, 4 at 0, 9. This point's nice. I'm going to move that up. 1, 2, 3, 4. This point is nice. I'm going to move that up. 1, 2, 3, 4. This point is nice. 1, 2, 3, 4. Nice. 1, 2, 3, 4. Nice. 1, 2, 3, 4. And nice. 1, 2, 3, 4. Okay, and that's going to, let me just make sure I have this. It's going to look now like that. Again, I just want to indicate that that's my function g of x. Okay, simple. Now letter D, this is kind of cool. The function f of x has only one zero. Algebraically determine its value. Now remember, to algebraically determine the value of a zero of a function, I'm going to take the formula for that function, which I've got right here. I'm going to set it equal to 0, and I'm going to solve. Now, that should strike you as being a little strange, right? Because this is a quadratic equation, and typically quadratic equations have two solutions, and yet I claim this one will only have one. Why don't you go ahead and find what that solution is, and I would suggest either using completing the square or factoring, and I would lean heavily towards using factoring to solve this particular quadratic equation. You could also use the quadratic formula if you wanted to, but I think factoring is the easiest way to go. So pause the video now and solve this equation using whatever technique you like. All right, well, if I factor, right, I'm looking for two numbers whose product is positive 9 and whose sum is negative 6. Well, those happen to be the same number, x minus 3, right? So x minus 3, negative 3 times negative 3 is positive 9, right? And negative 3 plus negative 3 is negative 6. But now, of course, if I use the zero product law and I set x minus 3 equal to 0, and x minus 3 equal to 0, well, that's a little silly. Add 3 to both sides, I get 3, and add 3 to both sides to this, and I get 3. So I'm thinking x equals 3 is my one and only 0. Finally, let's take a look at letter E. How does the graph of g of x support your answer to part D? Well, let's talk about this together. If I look at g of x, which is my graph here in blue, my 0 should be where it hits my x-axis, and that only occurs right there at x equals 3, right? So the graph supports it because the only x-intercept is x equals 3. That's it, right? Keep in mind, right, and we've talked about this before, a given parabola or a given quadratic function can have either two zeros, as the original one did, right? It had a 0 at 1 and a 0 at 5. Or it can have one 0 if it only touches the x-axis at that one spot. That's called being tangent to the x-axis. Or it could have no zeros whatsoever. For instance, if I had taken that original function and instead of moving it up 4, I had moved it up more than 4, let's say 5 units, right? Then it wouldn't hit that x-axis at all, and its discriminant from the quadratic formula would be negative. That's a little bit from that last unit that we did. All right, let's take a look at one more problem. Now, vertical shifting of functions can certainly have practical applications. This isn't just a, oh, let's do it all for the sake of doing it. There are practical reasons for doing this. So let's take a look at exercise number 4. A physics experiment is run where a projectile is fired from the ground surface. Its height, as a function of the horizontal distance it has traveled, is given by h of x equals negative 0.02x squared plus 1.6x. The graph is shown below. Letter A, using the axis of symmetry formula, it's been a while since we've seen that, show that the maximum of the function h of x must occur at x equals 40. Now, I get it, like that, the graph already is kind of showing us that the maximum is reached at x equals 40. But this is a good opportunity to review the axis of symmetry formula, right? The formula that predicts what the x coordinate will be at the turning point. Remember, that x coordinate will always be negative b divided by 2a, right? That is the axis of symmetry formula. Now, side note, when we looked at negative b over 2a back in, I don't know, I want to say it was Unit 8, when we were working a lot with quadratic functions, I just kind of tossed it out there to you. I'm thinking though now, it might look a little bit familiar because it's part of the quadratic formula, right? The quadratic formula was negative b plus or minus the square root of b squared minus 4ac divided by 2a. So there's that negative b and that 2a portion of the quadratic formula. Whatever. Is there a reason? Is there a connection? Yes. And you'll look at it more in Algebra 2. But for right now, I just want to plug these in. Now remember, b is the coefficient on x, that's 1.6. A is the coefficient on x squared, that's negative 0.02, right? So my axis of symmetry should occur at x equals negative 1.6 divided by 2 times negative 0.02. That's going to be negative 1.6 divided by negative 0.04. And again, I'm not feeling really like doing that without a calculator. So what do we have? We have negative 1.6 divided by a negative 0.04. And that is x equals 40. Right? Remember, that's that vertical line that cuts a parabola into two symmetric halves, right? So there it is at our x equals 40. All right, so we know that the peak height has to be at x equals 40. Now, that has nothing to do with the vertical shifting yet. Let's now talk about vertical shifting in letter B. The projectile is then fired off the top of a 15-foot tall platform so that its new height function is given by g of x equals h of x plus 15. Graph g of x on the grid. All right, so in other words, right, g of x is simply h of x that's been shifted up 15 feet. It kind of makes sense. If originally I fire it off from the ground surface, right, 0, 0, and now I'm firing it off from 15 feet above, right, it makes sense that the whole graph would just sort of shift up 15 feet, right? So what I'm going to do is I'm going to come in here and I'm going to take this. Now, 15 is literally, because my y-axis is scaled in terms of 5 units, it's going to be going up 5 scale units, right? So I've gone up 5 there. Maybe I'll take here and I'll go up going up, not 5, going up 3 sets of 5. So 1, 2, 3, it's just a little bit shy there. Here, whoops, come on. Here I can go up 1, 2, 3. Here I can go up 1, 2, 3. It'll top out about there. 1, 2, 3. 1, 2, 3. 1, 2, 3. And 1, 2, 3. Now, of course, I don't really know where it's going to hit because that's not part of the shifting at that point. But I can shift every other sort of point up by 15 units. All right, so finally, letter C, what would be the peak height of the projectile would reach that was fired off the platform? Justify your answer. So I'd like you to play around with this a little bit. Now, I can kind of see it's maybe somewhere between 45 and 50 feet, but I don't know exactly what it is. I do know, though, that it occurs when x is equal to 40, right? If its peak was at x equals 40 before, and I just shift everything up 15 units, then its peak should still be at x equals 40, but I want to know the actual height it hits. So pause the video now. You'll probably need to use your calculator and see what you get. All right, well, one thing I could do is I could find the peak height of h of x and then just add 15 to it. So let's do that, right? Let's figure out, we know that h of x was equal to negative 0 to x squared plus 1.6x. So let's figure out what h of 40 is. All right, I'm going to use my calculator here. Right, so h of 40 is going to be negative 0.02 times 40 squared plus 1.6 times 40. And that's going to be 32 feet. All right, so this is going to be 32 feet. But g of 40 will be h of 40 plus 15. So that's going to be 32 plus 15, which is 47 feet. And that is roughly what it looks like, right? Right around 47. Okay, let me put this back into full screen. All right, let's wrap this lesson up. Vertical shifting of functions. So simple. I add a number to the overall function, it shifts everything up by that amount. I subtract a positive number from a function, it shifts everything down by that amount. Because all I'm doing is adding and subtracting from the outputs of the original function, from the y values. So it makes sense that if I make all the y values increase by a certain amount or decrease by a certain amount, then I get this vertical shift up or vertical shift down. In the next lesson, we're going to be looking at shifting to the left and shifting to the right, which is significantly stranger and more complicated than the vertical shifting. But we'll get to that in the next lesson. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.